more than AI techniques. This effort's long-term goal is to establish a sustainable and scalable learning community. And this will be accomplished through the in-person workshops we are organizing in early next year, online self-paced learning, as well as our webinar series, which is happening now. And the Cyber 2A webinar series is co-created with the NSF Permafrost Discovery Gateway project. And our goal is to connect the Arctic scientist, geospatial scientist, AI expert, and our industry and community partners to foster cross-disciplinary conversation and innovation so we can best empower the next generation geo-AI scientists. And today we are very delighted to invite our two distinguished speakers, Dr. Paolo Fraccaro and also Dr. Daniela Szwarcman from IBM Research to introduce their new development in geospatial foundation models. Because this is also our training webinar, we have a poll to ask you one question about your familiarity with the GeoAI foundation models. Jiayu, would you mind launching the poll? And I will introduce briefly our distinguished speakers. Dr. Paolo Fraccaro is a distinguished data scientist at IBM Research Europe with extensive research experience in data science and AI applied to solve a wide range of scientific and business problems. He has contributed to the development and commercialization of key techniques and solutions, such as environmental intelligence suite and geospatial foundation models. Paolo's research interests lie at the intersection of technologies like AI and cloud applied to geospatial and sustainability, agriculture, remote sensing, healthcare, and more. He has authored several peer-reviewed journals and currently leads the development of scalable tools, pre-built workflows, and models to enable data scientists and developers to easily fine-tune and inference large AI models, which is very relevant to what is going to talk today. And Dr. Daniela Szwarcman is a research scientist at IBM Research as well. She received her PhD from PUC Rio in electrical engineering with a focus in AI. She has participated in many AI projects, mainly developing and implementing deep models for problems that involve spatial and temporal data. At IBM, Daniela's primary research interest is developing and applying deep networks in the context of weather and climate problems. Her research interests include deep learning, generative models, and physics-informed machine learning. Without further ado, I will leave the floor to both Daniela and Paolo.
Thanks for the invitation. That's really an honor to be the first ones in the series. Daniela will share the screen for now, and I'll just introduce what we did with NASA, IBM Research, and NASA, and then she'll go through some details on the GFM side of things. So this project really is a collaboration between these two institutions that have these complementary skills around domain expertise and data pre-processing and collection with NASA, and IBM also with the more AI and computational capability skills. And they came together with the idea of trying to build new foundation models that would allow basically to get insights from a large amount of geospatial information to increase the speed to which we can have impact on Earth observation and beyond. This talk really is focused on the Earth observation part of our collaboration, but there is also another one that just kicked off Q4 this year, so last month, that is working more on the weather side of things. Next slide. This is just to give you an outline of what we're going to talk about. I briefly talk about IBM and NASA collaboration, but I'll give you a sneak peek on the framework overview. Then Daniela will go deep on the actual foundation model architecture, the data we use, the way we pre-trained, and other details around that. Then I'll come back with some of the fine-tuning applications that we use this foundation model for, and then we'll go to Hugging Face. Hopefully you'll be curious and excited to use it by then, and the model is on Hugging Face, so I'll give you some info on how to try it out and use it for your own applications. Next slide. Next slide as well. So for people who are not familiar with the concept of foundational models, this is this new concept of having these big models, large models that has started in text with these large language models. People know GPT-4 or Llama lately, and so on, and they are really trained from broad data at scale, and then they are capable of being adapted to a wide range of very specific downstream applications with usually much less effort and often with state-of-the-art performance or beyond. So in this collaboration, we next slide, we apply the same approach that has been proven successful with text to geospatial information. And I gave you the context on how these two institutions come together. And the focus of this collaboration was on one of the NASA data products that is called Harmonized Landsat-Sentinel 2, HLS, and Daniela will give you some more details about that. And the idea under the pledge of open science was really to do something that then the community could use as well. So it's on Hugging Face. Next slide. Just a sneak peek of the framework that we are going to go through, right? So as we said, these models are trained on a large amount of data at scale. So if we think on the left, we have a general geospatial data source. For us, it was HLS. Then we are going to sample a representative and big amount of information. The model that is on Hugging Face has been done for the continental US, but we are working on taking that globally. And then once you have sampled, you can filter out and pre-process. For example, if you're not interested in things like cloud coverage and so on, you can filter them out, or specific areas. And then after that, you can produce your training examples. Zara is what we used. And we use this self-supervised learning approach that Daniela is going to tell you about. At this point, in this step, what we do is pre-training this encoder part of the foundation model that basically can be reused with on supervised learning approach that classically can be basically implemented only with labeled data, and that's why this concept of foundation model is so popular, because you need much less labeled data and to actually have something meaningful for a specific downstream application. And then once you have trained the model for the specific downstream application, you can, with the same geospatial data source, then make inference or use the model for real for a different application. So depending on how you're familiar or not you are on each of these specific boxes, this might sound a little bit difficult for now, but we're going to go now through each of these boxes between me and Daniela, and hopefully by the end you'll be familiar with all of them. So with that, I'll just leave it to Daniela for now.
Hi everyone, I'm Daniela, and now I'm going to talk about our geospatial foundation model, which we call Prithvi. Well, so let's start with the data source for pre-training our model. The Harmonized Landsat-Sentinel 2 data, or HLS, is a product from NASA that provides consistent global observations of the land at a 30-meter resolution. So the data is available in tiles, which means that the globe is divided into regions of about 110 by 110 kilometers, and we can access these regions individually as images. In terms of image sizes, these tiles, they have 3,660 pixels on each side, and the data is stored as GeoTIFF files. So for each available date, we have one file for each spectral band. Given the redundancy in satellite data across years and regions, it wouldn't be efficient to train a large model on all the available data. In other words, for a given region, the images can look very similar across time, or different tiles can represent very similar landscapes. So to ensure a high quality training setup, we need diversified data that is representative of the landscapes. And to reduce the redundancy across regions, we could think about doing some random sampling, for example, over the available tiles. However, random sampling could result in biases toward the most common landscapes, and the less common landscapes would be poorly represented. With those issues in mind, we developed a sampling scheme based on geospatial statistics. So the first step of the sampling procedure is to aggregate geospatial statistics. Essentially, it could be any statistic that can serve as a proxy for different landscapes. So here I'm showing an example where we used temperature and precipitation statistics. So once we have those statistics aggregated, then we divide the region of interest, in this case, the US, into groups based on these statistics. Here on the left, we can see such groups. I think the colors are somewhat similar. I think we have something around 20 to 30 groups. And finally, we sample the HLS tiles as equally as possible from each group. So the assumption is that we have similarity between regions of these groups. Another intrinsic issue with satellite images is that they can contain significant parts filled with clouds, meaning not showing the land at all, or missing values, as you can see in this example here. And therefore, to ensure high quality data for training, we must filter out those problems. The HLS data actually provides a cloud mask file for each tile at each available timestamp, showing exactly where the clouds are in the images. So this means that we can leverage that information to compute the percentage of clouds and also missing data in each tile. Then we can select only subregions that are cloud-free and with no missing values, as in this yellow square in the picture. Since the HLS tiles are very large images, we can get many smaller subregions with good quality from each tile. So this filtering, although it is a straightforward process with the cloud masks, would be too slow to run during pre-training, as is, of course, it must be conducted for all the tiles and time steps available for our training data. Therefore, we developed an offline procedure to separate the good quality regions before pre-training. So the procedure is simple. So considering that the input image size to the model that we want to train our model with is X by Y pixels, we divide each HLS tile into non-overlapping windows of size X by Y. Then we compute the percentage of pixels containing missing data or clouds. We define a threshold to filter out the subregions that do not respect the conditions. And we then save the indices or the locations of the good quality subregions in a file so they can be easily accessed later. So once we have the good quality indices in a file, we can use this information to load the subregions from the GeoTIFF files and build the input samples during training by cropping the good quality sub-images. So basically we have here the list of indices of locations, and here we have the spectral bands for one time step, and then we just crop the good quality subregions for all the images, and we then build here one sample for date T. However, if you think about building a batch of examples as we train the model with batches of images, if we think about that, we actually need to load a lot of files, which can result in slow data loading to the model and poor use of computational resources. For instance, if we think about a batch of 128 examples composed of 3 time steps and 10 spectral bands, we would have to open 3,840 files. So that's actually a lot. And if we need to stream the data for training, this also means that we need to download the entire GeoTIFF files, even though we only load a portion of those files. So considering all these issues, we decided to go with an alternative approach. We save the good quality subregions in ZAR files to leverage its efficient I/O capabilities for pre-training. So this is actually an additional pre-processing step. The procedure, again, for this pre-processing step is simple, as it basically requires reading the list of indices in the file, loading the subregions from the images, and just saving them in the ZAR files. However, since it needs to run throughout the entire training data, we developed a parallel and cloud-native process to do this efficiently. The data loading scheme actually becomes quite simple as the data in the ZAR files is already in the format and shape that we need to pre-train the model. So we just read the files. We don't need to do this cropping and building because we already did that. And we just read the files, the ZAR files directly. So just so you can get an idea of the performance, here I'm showing the epoch average time for 2 pre-training experiments we conducted on 8 GPUs with the exact same model and data. The difference is just the data loading scheme. So the first line, we have the GeoTIFF loader where we load the GeoTIFF files and build the samples. And in the second line, the ZAR loading scheme, where we just read the ZAR files. The data is already pre-processed in the shape that we want. And as you can see, the ZAR loading scheme is almost 2 times faster than the GeoTIFF one. Well, so now that we know about the pre-training data source, moving on to the model itself. So similar to what is done for text and natural images, we train the geospatial foundation model with a self-supervised approach. More specifically, we use the popular task of image reconstruction in masked image modeling. So it works like this. We take an input image, divide it into patches, we randomly mask some of these patches, usually with a high ratio. And notice that the masking occurs at the patch level and not at pixel level. A patch can be either fully visible or fully masked. And then we train the model to reconstruct the original images. So the target of this pre-training task is exactly the original image. We don't need additional labels or annotation. This is a self-supervised task. So we compute the MSE loss, or mean squared error, between the target and the reconstructed image. Regarding the model architecture, our model is based on the masked autoencoder, or MAE approach. And in the model, actually, it has two parts, the encoder and a decoder. The encoder receives the image patches, in this case, only the visible patches, and extracts features from these patches. So the blue squares represent the encoded data. The decoder receives both the encoded data and also the mask tokens in the correct order they appear in the image. And then it reconstructs the original image. The decoder is responsible for generating the whole image, all the patches. However, the MSE loss is only computed for the masked patches. So the idea behind this is that if we train the model in this way with a large data set, the encoder becomes really good at extracting relevant features for the data. And this is what we leverage when using the model for a downstream application. So once training is done, we can replace the decoder with any suitable set of layers, like classification layers, segmentation layers, object detection layers, or any others that we want, for a specific downstream task, and fine-tune the model for that particular task. So going to a little more details on our architecture, it considers the multispectral and also the temporal aspects of remote sensing data. So this means that our foundation model can be trained on sequences of HLS images with several bands. So the original MAE approach uses a standard vision transformer as the encoder, and the decoder is also a series of transformer blocks. We followed the same idea, but we implemented 3D patch embeddings and also 3D positional encodings, so the model can consume a sequence of satellite images. So we considered that this is important because we want our model to learn a data representation that also considers the temporal aspect, the sequence of images, as this is essential for several downstream applications. So here I'm showing some training details for the model that is available on Hugging Face. So the input sample for the model is a sequence of 3 square images of 224 pixels each side. And we get these smaller images from the large HLS tiles. I mean, the good quality regions is 224 pixels by 224 pixels. In particular, this model was trained with data sampled over the US, but we can expand that as well. And our model is trained with 6 bands from the Landsat part of the HLS, meaning the RGB bands and also 3 infrared bands. We selected these bands because they are already useful for many downstream applications, and they also overlap with Sentinel-2 bands. But the intention is always to get more bands included. So as usually done in the literature for these types of model, we mask a high percentage of the input sample. So 75% of the patches are masked. And the idea is that the high masking ratio, it will promote better data representations, meaning that the model in this case will learn more high-level information, which is more interesting, instead of simply completing the images with detailed structures. We can have different algorithms for masking rather than randomly choosing patches to mask. For example, we could mask a big square in the center of the image, for example, but evidence from the literature and our initial tests indicate that random masking is usually a good choice. The model that is released on Hugging Face has about 100 million parameters, and we trained it in the IBM Watson X platform. And one thing I want to highlight here is that our input sample is large if we compare to text data and also to natural images benchmarks that we usually see large vision transformers trained on. So we have, compared to natural images, we have the temporal aspect and also more channels. We don't have only RGB. On the IBM platform, using 64 GPUs and 512 CPUs, it took about 4 days to train this model. So here I'm showing some reconstruction results, just because it is interesting to see the performance of the model on the pre-training task itself, right? So how well the model can predict the masked patches for data it never saw during training. So here we have 2 reconstruction results for our model. And I'm showing here only the RGB channels just for better visualization, but it predicted the 6 bands, right? The first column here shows the original image sequence, the sequence of frames starting here at the first row. And here we have the masks applied, the random masks applied. And finally, here we have the images predicted by the model. And in the last column, the mix between the visible patches and the predicted ones. So let me show here some interesting aspect of this. And if you look here at this green circle, you can see that it remains green in the second time step, but it changes color in the last time step. And the masks, they partially hide the circle in all images, but the model is able to complete it with the correct color. Also here on the right, we can see that the model completes the relief lines in a reasonable way. So here is, I'm showing a slightly different result. The model was trained with 75% of masking ratio. And here we can see that how the model does for different masking ratios on unseen data. It never saw this data during training. Specifically here, I'm showing bands 6 and 7 infrared bands. So even with higher masking ratio, in this case 90%, the model still predicts the masked regions in a reasonable way. It is more blurred, this is expected, right? But we don't see any aggressive changes in pixel values, meaning that the colors are still reasonable here. And this indicates that the model could generalize to other masking ratios, which is a good sign in terms of its capabilities. Of course, these are just an initial evaluation of the pre-trained model. To actually see if the model has value, we need to fine-tune it for several downstream tasks. So now I'll pass over to Paolo so he can better explain some of the fine-tuning tasks we have tested.
Let me share my screen. So you should see my screen, hopefully. Yeah, of course, after having pre-trained the model, then the key point is how leverage it in impactful downstream applications and hopefully doing things easier and quicker. So I guess just to put everything together on how we leverage the model after we understood what self-supervision is and what we are actually training or we're interested in training in the self-supervision approach. So we have a reminder at the top of this slide. Then after we have trained the foundation model, geospatial foundation model, at the top, what we want to actually reuse is the encoder, to which we are going to put, in this case, a segmentation head, because we're interested in flood mapping, for example. And then in this case, we perform a pixel-wise classification where the features, these relevant features, this time the image is not masked out or anything like that. It's just the actual image with all the different bands and all the different patches available to the model. Then this information is passed through the encoder, and we're able basically to customize it with some labels to a specific downstream task. In this case is flood mapping. As part of the collaboration, and people might have seen that as part of our technical paper that was published a couple of weeks ago jointly with NASA, we have done these downstream applications. So we have an encoder, common encoder, and then we applied segmentation head, in this case binary segmentation, semantic segmentation for burn scars detection and flood detection, and also a multi-class semantic segmentation, actually multi-class, multi-temporal semantic segmentation, meaning the first couple of use cases leverage the model in a different way. So we trained with 3 timestamps, and we just use a single timestamp. In this case, for the crop classification, we use 3 timestamps, and then data imputation. Data imputation is fairly similar to what we have done in the self-supervision. So imputing data where it was missing, but we were masking out. In this case, is for cloud gap filling. So I'm gonna go through some of these just to give an idea of the results. So the first one I'm gonna go through is flood mapping, and I'm describing here the data set that we used. This is we can't say a benchmark data set, because at least for flood detection is one of the most widely used. It's called SAN1 Floods 11. The interesting thing about this data set, and we picked it because with NASA we wanted to have some relevant applications that relate to climate change and changing environment, and similar applications. But this shows that the model, despite being trained on HLS data, that yes, has Sentinel-2, but the resolution is 30-meter resolution, can actually adapt to 10-meter resolution, because this data set has Sentinel-2 as the main resolution, so as the main input data source. So the data set contains single timestamp Sentinel images, so there is also the Sentinel-1 data as well. But we haven't used, we just used the relevant bands for S2. For 11 flood events around the world. So this is interesting because it also shows the model different areas of the world that hasn't seen yet. And the labels contain manually annotated water extent. So you see an example in the bottom row, and it's fairly small as well. It's about 450 images, and the train was done on around 250 images as well. So you see at the bottom the table with the results, and we trained basically a range of comparison state-of-the-art architectures, and in the end, basically after 50 epochs, the model, the pre-trained model, so not pre-trained means that we randomly initialize the weights with the same architecture that had those tweaks to handle this spatial temporal context that Daniela explained. And the pre-trained model is still better. This is under after 200, and then they basically converge, but it takes a very long time. So they're basically the same in terms of performance on this data set, in terms of intersection over union, and F1 on the water class. So the other thing that we are seeing here is how this model can be used, in practice. This is something that we have been working just on the IBM side, trying to make these models available, also through our new platform, watsonx, where we have basically the chance of operationalize these models at scale. In this case, we see the input image that was retrieved from our geospatial database. Then the model is applied with the red being the flooded area. So despite this is a fairly localized flood in this small area, the model does a reasonably good job at identifying the flood, even in the middle of those urban areas, which is fairly difficult. And then this is just an impact where in dark purple we have the urban areas affected by flood, in dark brown the crop affected by flood. So this is just to make it a little bit more meaningful and show an example of how this might be used in practice. The other very interesting thing, the accuracy was in the end very similar. At some point when there are so little differences, is difficult to differentiate. But the interesting thing is actually saying that after 5,000 iterations, which is not a lot overall. So these iterations are the batches. So there is still a long way to go. The pre-trained model is actually already up there, close to peak performance. Instead, the randomly initialized model, this is in terms of IOU, is going to take quite a while to get there, and we have seen after 500 epochs is going to converge. The other ablation study that we have done is actually reducing the amount of information that we give to the model and see how the performance drops. And in this case, the regional fine-tuned data set, and you see here confidence intervals, because we have done for this experiment this 5 times. So there is some confidence interval on this result. We show that for this data set, and this is valid for this data set, and I'll show you some results later on another one. We cannot say that is going to be the same for any task, but for this specific task that is very visual, and then there is a clear signature in the data, even reducing the data, the training data, so those 250 images by 87.5%, we don't see a huge drop, which is really good to see for what we wanted the model to do. And the other thing that is interesting, there was an external assessment of the Prithvi model by some researchers in the US, and it shows that on the same data set, so San Juan Floods 11, they trained Prithvi, and they trained also SegFormer and UNet. In this case, UNet was slightly better on the test set, while Prithvi was better than SegFormer. But the very interesting thing for us, which was actually really nice to see, was the San Juan Floods 11 dataset has an out-of-sample country or event that is taken basically out from the train-val test splits, which is Bolivia. And in this one, actually, Prithvi does much better than the other models that were tested. So this is, I guess, a validation, although small scale in this case, because it's this specific example of the value of having the model that was pre-trained and can basically extract relevant features and handle unseen data. The second use case that we have worked on with NASA was burn scar detection, and the data set was basically coming from monitoring trends in burn severity initiative, manually screened by NASA researchers to make sure high quality data, and also that there would be available data in terms of HLS, because there could be cases in that data set where they might have an extent, but you don't have an HLS image before they have replanted, for example, if it was a plant burn of a specific area for agriculture, for example. So the data set was manually screened and is available on Hugging Face. In this case, resolution is 30 meters, and is a single timestamp as well. In this case, it's slightly bigger than the one before, so about 540 train samples. And we see in this case similar results where Prithvi is slightly better than the alternatives that we tried. And again, we see that for this specific use case, we have very good coverage of this burn scar, and in dark green you can see the trees affected, so the forest affected by fire. Similar story for the ablation studies, where we have the pre-trained model that takes much less to get to close to peak performance. In this case, the only time where there was really a very bad reduction in performance in terms of IOU when we reduced the amount of data was 87.5% reduction, where we were giving the model just a few images and it couldn't handle it. But for the rest, let's say it wasn't peak performance, which would be here, but it wasn't very far. And the last one, this one, collaborators from Clark University work with us as well, and they focused on cloud gap filling, and for continental US, again, 30-meter resolution. That's a data set that they created, manually created. And it's interesting because this is multi-temporal as well. So is a data set where you have HLS images with a various amount of clouds and 3 timestamps that can be 1 to 200 days apart. There is at most 5% of cloud coverage in each of those. in this case, the data set was a bit bigger. So we have about 6,200 images that were used to train, and the chip was the original chip that was used for pre-training. In this case, the comparison was with the CGAN, which is a state-of-the-art alternative to doing this sort of application, and both in terms of mean absolute error, we see that the validation error of Prithvi is better than the CGAN alternative, as well as for the structural similarity index measure both after 200 epochs. So I rushed a bit through it just because I saw that we are close to time, and I wanted really to go through the Hugging Face org page that we have. So this is where you can find the pre-trained model and some of these use cases that we have done with NASA and Clark. So if you wanted, for example, the weights for the models would be in this section. If you wanted some of the data sets, also would be in this section. There are some nice demos. There is the link to the technical paper, and the other thing that I wanted to flag, that there are links throughout, is this open source code to either load the model and run inference on it. There are instructions on how to do it, or fine-tuning the model to your own applications. And everything is brought together. That's something that we just added actually this week, or last week, sorry, in this notebook where it explains how to set up your environment, the relevant inputs. There are some visualization functions that we provide, but you know how to load the foundation model, and all the way to the end to use the flood detection model for a specific tile, and then how to fine-tune to your specific application. So with that said, I think me and Daniela are done, and with the time left, we are really happy to take any question. Thanks for listening.
Thank you, Paula, Diana. This is a very informative presentations. So just like a personal note, we have been seeing a lot of development in terms of the general AI foundation models, and we have been waiting for our first geospatial foundation models, and here it comes. So we're very excited about its model, its result, and also its open source nature. It really helps us to grow the community for building this future AI models for geospatial applications together. Thanks so much for doing that. Okay, so we have a few minutes for question and answering. I see there are some open questions in the Q&A. Paolo and Diana, do you guys want to?
Yeah, sure. So Daniela, maybe there are quite a few around pre-training, if you want to go through those ones. For example, the one at the top, at least the one that I see from Tom.
Okay, I can go to that one. I mean, yeah, this is a good question. I mean, why did you choose mass image modeling as the self-supervised pre-training task and not contrastive approach? I mean, I think this is an open discussion. There are people that advocate in favor of mass image modeling. There are people that advocate in favor of contrastive learning. But so far, at least from my perspective, my personal perspective, mass image modeling has been the most widely used for image applications, I guess. In this space of foundation models, right? So that's why we started with that. And I don't think it has much more. I mean, I personally haven't seen many good discussions on that, but from the literature, usually on those papers about foundation models and images, mass image modeling has been more widely used, I would say. Maybe it's just because it's easier to implement, but I don't know if there is some like very thorough studies on which one is the best one.
And the idea is really to, you know, keep improving and taking feedback from the community as well has been also one of the reasons why you know, as was said, we grow and we can build on it and so on, right? So this is the first iteration, and we're working on improving as well. For example, I see another question that is around the use of Sentinel-2 data rather than HLS data. So in terms of downstream applications, if you mean going even higher resolution than 10 meters, that can surely help. I believe. In this first phase, we haven't done it, but we're trying to bring in the next phase, not Sentinel-2 per se, but at least S10 as you know, the HLS related product to Sentinel-2, which is then the one that is going to be transformed in S30. Because there is some pre-processing that they do to make it comparable. So if possible, we would really like that. S10 is not openly available as far as I understand, but obviously working with them, with NASA, this might be possible. We're trying to figure that out, but that's an early good comment. Think about assess, prove data sufficiency and representativeness for this foundation model. Do you want to take that one, Daniela?
Yeah, that's again a good question. I mean, it's a hard thing to prove, I guess, but the best way I think to assess its quality is test it all over the place. I mean, just I mean, with all kinds of downstream applications, with all kinds of not kinds of, but all regions possible. I mean, I think that's the best way to assess at least the capability of one model. However, I acknowledge the difficulty in comparing models in that perspective. But yeah, it's hard because you train the model with this pre-training task, which is not exactly what you do for the downstream application. So that's why it's kind of indirect, right? So you need to use it a lot, I would say, to see, okay, this model actually has value. So I would say the best way right now is just to use it in several downstream applications and in different regions.
I noticed that the decoder head. I'm curious about the reasoning behind choosing specific decoder heads for each task. So in terms of the different decoder heads, I didn't say, but as part of the framework, there is the chance basically to iterate over. It's not really hyperparameter tuning, I wouldn't dare saying, but there are different options that can be tried for different heads that are compatible. So in a simple way, we can basically have a test and see. I don't think that we are yet in a place where with a super simple head you can handle everything like philosophically maybe you would like to do with foundation models. I think we're getting there, but we're not there yet. So for some applications you can still have some good gains, maybe spending a little bit more time, and we have identified 2 or 3 different hats that we could try on the different applications, at least for segmentation. So that's why we wanted to make them available for you know, the different people that have done the fine tuning.
So there is one question about the value of pre-training from Craig. It seems that the performance differences between the pre-trained and the non-pre-trained versions are pretty small. Then what would be the advantage in terms of pre-training?
So the advantage is for sure the speed up, and I think also, and we had the glimpse with that external evaluation, but as Daniela said, we need to do more to fully prove it, is really the generalizability that hopefully happens through having learned how to extract these features around the world. And as I said, Craig, as a journey, and I really hope that you know, at some point we'll get to prompt tuning and zero shot, all those things being very easy based on foundation models. I know that there is work already, but it doesn't feel like we are there yet. And then the value of pre-training will be much more evident. At least this is my opinion. Daniela, do you have anything to add?
Yeah, I totally agree with that. I just wanted to add one point of view, an extra point of view about the volume of data, right? Because depending on your downstream task, you might not have the data sufficient to train your model from scratch. So sometimes you need to, it's not only about speed up, but it's about having a model that already knows something related to that downstream application, and then you can use your small data set to train that model. So that's also a value of pre-training. But as Paolo said, we hope to keep improving the model as well, and hopefully this model will be better and better over time.
And not just ours. I think the community is taking an interest this year.
Yeah, I think I really like the term of it is a journey, and thanks for doing so much like exciting work for the whole geospatial community. And I see this talk has raised a lot of interest. Some of the questions we were not able to answer within the hour, but we will try to collect some answers from the presenters for you. And we also have a poll for some follow-up activities, like a potential for a hands-on workshop. We hope we can get the feedback from you and then continue to organize our webinars around this exciting topic. And Paolo and Daniela, there is a question about sharing the slides. Do you think
that we need? I don't think there is any particular reason why we couldn't, but we need to ask internally at least. But so except for the very pretty slides that Daniela has done to explain the whole pre-training, the rest is in the technical paper, so you can really get access to all the content based on we can share the link, but if you go on the IBM NASA Hugging Face page, at the end of the intro there is the link to that paper, so you would have basically all the content and info, and possibly a little bit more info as well.
Yeah, I just also shared the link for the paper on the chat. Okay, I think we're at the top of the hour. Thanks everyone for coming, and we look forward to seeing you and continue our discussion on geospatial foundation models. Thanks so much for our distinguished speakers for your excellent presentation.
Thank you very much.
Thank you very much.
Bye.
Bye.
It was an honor. Thanks. Bye-bye.